Hello, everybody. My name is Qing Yang. I'm assistant professor in Brandon University. Today, I will represent my paper, Bayesian Soft Actor-Critic, a direct, acyclic strategy graph-based deep reinforcement learning. And I will separate 4 parts to introduce this paper. First, let us have some background knowledge about this research. In artificial intelligence, a strategy describes the general plan of an AI agent achieving short-term or long-term goal under conditions of uncertainty, which involves setting sub-goal and priority, determining action sequence to fulfilling the task, and mobilizing resources to execute the actions. In reinforcement learning, a strategy is the rule used by agents to select an action to pursue goals, which is the equivalent to a policy in a Markov decision process. The policy indicates the action that the agent takes as a function of its state and the environment, and the goal of the agent is to learn the policy, maximizing expert accumulative the reward in the process. With advancement in deep neural network implementations, deep reinforcement learning helps AI agents master more complex strategy and represents a step toward building autonomous systems with a high-level understanding of the virtual world. Especially the deep reinforcement learning is ideal for robot manipulation and locomotion because there is no predefined training data requirement. Furthermore, the control policy could be obtained by learning and updating instead of the hard-coding directions to coordinate all the joints. There still have some challenge in deep reinforcement learning currently. In most cases, complex strategy and system usually consist of the multiple tackles or subsystems governed by corresponding sub-policy, which represents a joint policy in real-time interactions. Second, a single strategy might involve learning several policies simultaneously, which means the strategy consists of several attacks and actions executing a task, especially in robot locomotion and real-time strategy game domain. Last, although achieving some progress, deep learning still hard to explain formally how and why randomization works, which brings the difficulty of the design efficient model expressing the relationships between various strategies. The second part, we will briefly discuss our approach. First, let us have some preliminary knowledge about our approach. The first is the Bayesian network. A Bayesian network is the probability graph model for representing knowledge about an uncertain domain, where each node corresponding to a random variable and each edge represents the conditional probability for corresponding random values. Second is the soft actor-critic. SAC is an off-policy actor-critic algorithm that can be derived from maximized entropy variance of the policy iteration method. It used an entropy regularization in its objective function, which trains the policy to maximize a trade-off between entropy and expert return. So for our method, we introduced incorporation of the Bayesian networks to decompose a complex actor into several simple sub-actors or sub-policy termed as a Bayesian strategy network. So the red picture, I just give you guys an example of the robot dog model using BSN. Then we integrate the idea of the maximized entropy reinforcement learning framework in SAC, design the method that result in our Bayes' soft actor-critic approach. And the red picture is an example of the proposed BSN-based implementation of the actor-critic DRL architecture model. So for our model, the objective functions for each sub-policy evaluation step of the solved policy iteration. The joint policy phi will calculate the value to maximize the sum of the subsistence pi's entropy in BSN using the below objective function. And consider that the evaluation of each sub-policy applying the same Q value and weight. The solved state value function can be represented as below. And the joint policy parameters can be updated by minimizing the expert KL divergence. Last, the loss functions. The soft value function is trained to minimize the square resident value of each sub-policy in BSN. We define the loss to be the expected value of the mean square TD error caused the sub-policy as below. Next, for the evaluation, we choose the OpenAI Gym Juco as the experiment test bed. And we compare the performance of the proposed BSAC agent to parallel technology on a range of the challenge continuous control tasks from the OpenAI Gym benchmark suite, like the hop, work2D, ant, and humanoid. And this is our experiment result. The quantitative result attained by the BSAC in our experiment indicate that both the sample efficiency and the stability of the BSAC on these benchmark tasks exist the state of the art. We also conduct an ablation study on one typical Majorco environment, Ant V4, which is the adequate to show the influence of different parts and the parameter of the BSAC. Last, I will give the conclusion for our research. So for this research, we introduce a novel agent strategy decomposition approach termed Bayes strategy net to achieving efficient deep reinforcement learning. Based on the SAC algorithm, we propose a new DRL model termed as the Bayes soft actor-critic, which integrates the BSN and form as a joint policy better adapting the Q value distributions. So for the future research, I list the three directions. First, for the multi-agent system, we want to implement our approach in the multi-robot system and the self-driving car. And for the real-time strategy game, we want to implement it in the StarCraft 2 and OpenAI video game environment. And for the robot locomotion, we want to implement in the Unitary Go 2 and local board WX250. So this is my presentation. Thank you much.